All right, folks. In this lecture, I want to talk. I want to kind of take everything we've been talking about and then to use to discuss about active transport, which will then lead me into the next topic, resting membrane potential. But basically, in the last few video lectures, we were talking about how basically solute substances, molecules, move across semi-permeable membranes, okay? And remember, just a little bit of review of the lingo here. Remember, in order for, actual movement to occur, there has to be some kind of semi-permeable membrane. Remember, we said that in the body, that cells have a semi-permeable membrane, that lipid bilayer, the phospholipid bilayer, the cell membrane, the plasma membrane, okay? And remember, when we say semi-permeable, that means it allows the movement of some things to move into or out of it and not others. Okay, so for example, if we've got, I'll just keep using the same example that I'm using. If we've got sodium on the outside, sodium on the inside, okay, and let's say we've also got potassium on the inside, potassium on the outside, all right, and we'll say that green, okay, is going to represent a potassium gate. All right, and then we will say blue is going to represent a sodium gate. All right, so now let's say in this cell here, all right, let's say we put this this colored gate in here. Let's say this is the only gate that's on the cell membrane. Okay, this cell, and we open this gate. Okay, sodium is going to be able to move into or out of the cell, but potassium will not. Because remember from previous discussions that we've had, these gates, these channels that facilitate diffusion, okay, they are very, very specific to whatever is going to be moving through them into or out of the cell. Okay, so that means if this is a sodium-specific gate, only sodium is going to be traveling through that gate into or out of the cell. Potassium, calcium, magnesium, glucose, amino acids, whatever whatever other substances you can think of will not pass through here. Okay, so keep that concept in mind. All right. Now the other concept, again, I just want to refresh your memory on is concentration gradient. Okay, remember that a concentration gradient is basically, to simply put it, is a difference in the concentration across the cell membrane, meaning if we want to create a concentration gradient for sodium, okay, there would have to be an unequal distribution of sodium on either side of the membrane. Remember, in the extracellular fluid, the intracellular fluid. Okay, so basically, let's say there are 100. Let's kind of stay with the same numbers I've been using. Let's say there's 150 sodium ions found in the extracellular fluid outside of the cell, and let's say, just with the sake of the talk, there are 5 sodium ions on the inside. You have now created a concentration gradient. Okay, there's a difference in the amount of sodium between the outside fluid environment of the cell versus the inside fluid environment. Okay, so now all we have to do then is take this sodium-specific gate, through whatever mechanism we use, will stimulate this gate to pop open. Okay, and if this gate opens, sodium is going to pass through it. And remember, if we're just talking about passive transport, okay, or passive movement, like just regular diffusion or facilitated diffusion that we talked about in previous videos, okay, this sodium is going to move down its concentration gradient. That means it's going to move from an area of high concentration to low concentration. So that's what we're saying here. Our sodium ions are going to travel inside the cell. We would call that an influx of sodium. Okay, if it was moving out, we would call that an efflux. Okay, if it was moving out, but obviously there's, that's not going to work out because of the concentration in the situation. Okay, and remember, let's say, again, for the sake of discussion, we leave this gate open. Okay, it just stays open. All right, sodium will continue to travel into the cell until we reach an equilibrium, meaning until we reach an equal concentration of sodium across the cell membrane. When there's an equal amount on the inside versus the outside, there will be no more net movement of sodium. Okay, but like I said, in the body, these gates don't stay open and they just don't stay open all day. They open and they close very, very rapidly. We'll talk more about that later on. Okay, so again, I just want to review that stuff real quick with you before I start talking about active transport. Okay, because active transport basically is the opposite of everything that I've discussed in the previous videos and everything that I just reviewed right here. Okay, so if we want to simulate active transport, all right. So again, let's just draw the cell here. All right, let's say this is a piece of a nerve. All right, let's say that's part of a nerve. All right, and let's say there are, I don't know, let's go with the numbers here again. 150 sodium ions on the outside. 5 sodium ions on the inside. Let's say there are 145 potassium ions on the inside and, I don't know, 5 potassium ions on the outside. Okay. And again, just to, we'll keep with our color code here. I do maybe. Okay. So again, remember, for the sake of this discussion, blue represents the sodium specific gates. Okay, and green is going to represent the potassium-specific gates. Okay, so let's say, for the sake of this discussion, that these gates are, let's say these gates are closed. Okay, now you guys know that nerves are electrically active tissues. Okay, you know that even before taking any kind of biology class, you always hear about this all the time. Nerves sending electrical impulses around the body. Okay, now basically when nerves do this, these electrical impulses, i.e. action potentials, are created when sodium and potassium shift across the cell membrane, their concentration. Okay, so basically, and we'll talk more about that in a little while, but let's say we just had a bunch of sodium move in and a bunch of potassium move out. Okay, we want to be able to reset these concentrations back to normal so the cell can recover from the events of generating an electrical impulse. Okay, but like I just previously mentioned, if we pop this sodium and potassium gate open, they're not going to stay open for very long. Okay, they're not going to stay open for very long at all. So as a result, okay, so they're going to close almost as quickly as they open. So, like I just said, only a little bit of sodium is going to move in and only a little bit of potassium is going to move out. Okay? So, but in order for the cell to fully recover, it has to restore this membrane potential. All right? It has to restore these concentrations. So there's another kind of pump. Okay? There's another kind of pump with this nerve cell that uses what's called active transport. All right? Now, basically, we call this active transport because we're moving against, I'm just going to abbreviate this, concentration gradient, CG. Okay, so active transport is moving against the concentration gradient. Okay, so let's say we had 10 sodium ions move in, so there's 140 on the outside. Now there's 15 on the inside. All right, and let's say we had 10 potassium ions move out. So now there's 15 on the outside and now 135 on the inside. And we want to reset this back to our original concentrations. Okay, that's where this active pump is going to come into play. Okay, but remember I shared with you one of my old professors would teach to us the ping pong ball analogy. Okay, remember, if you have if I take a bunch of balls, stack them up on the ceiling, okay, and I punch holes that are just big enough for the balls to fit through, all right, they're going to fall down, especially if there are no other balls, below the ceiling, all right? So that is simple diffusion. All right, now, if we want to put the balls back up in the ceiling, okay, they're not going to magically do this on their own, all right? You're going to have to physically pick the balls up, you're going to probably have to stand on a chair or a table, and you're going to have to place the balls back up through a hole into the ceiling. Okay, so you're working against the concentration gradient. Okay, now when we say work, we're saying you're expending energy to try to, physically do something. Okay, so same thing here. All right, you know that by the natural laws here that that when it comes to the movement of molecules or water or atoms, they move with the concentration gradient. Okay, so in order to pump sodium back out to restore the number back to 150 on the outside and the number back to 5 on the inside, that's going to require energy. All right, that's going to require energy. So as a result, we're going to burn ATP. All right, that's where the energy is coming from. Okay, so sodium is going to pump outward, and then at the same time, potassium will also be pumped back in. Okay, again against the concentration gradient. Okay, so that's basically active transport. Okay, burning ATP to move molecules against the concentration gradient. Okay, and this happens in quite a few different tissues of the body. Okay, you'll learn about this when we talk about the physiology of a muscle contraction as well. Okay, when a muscle contracts, all right, you have to move calcium around within the muscle cell. Okay, and when we want to store calcium, when we want to move calcium back to where it's stored in the muscle, we're moving it against the concentration gradient after the muscle contracts. That requires the burning of ATP as well. So anytime you're moving from an area of low concentration to high concentration, that's going to require cellular work, okay? And again, that work comes from the result of snapping the chemical bonds that hold ATP together. Okay, so, and this pump here that I just described is called the sodium potassium pump. Okay, for sodium potassium ATPase. Remember, when you see the letters ASE at the end of a word, that means we're talking about some kind of an enzyme. Okay, it takes an enzyme to snap this chemical bond so energy is released and we can perform work. Okay, so that's basically active transport, the opposite of everything that we just discussed. All right, now what I want to do is, I'm going to do this in another video, is I want to talk about one of the most core aspects of physiology, the resting membrane potential. All right, I'm going to introduce this topic to you now because when we get to the nervous, because one, it's a big application of everything we just discussed in all these different videos, and two, we're going to come back to this when we talk about nervous tissue. When we start the nervous system, and the first thing we talk about is nervous tissue, we're going to talk about the physical actions that take place of how a nerve actually generates an electrical impulse. All right, and that's again is an application of all of this. Right.